Now let us move on to systems. Again, this will follow very similar path compared to continuous time systems. So we are going to define what a system is, what the system properties are, and then later we will focus on one particular subclass, namely the class of linear time invariant systems. Exactly what happened along the lines of in signals and systems. But there you focused only on continuous time systems. Now we will focus on discrete time systems, and in LTI we will again revisit convolution quickly. It's very similar to continuous time convolution. Again, we will point out some of the properties or some of the observations that you may or may not have taken note of or made a note of before. So let us look at systems. So for this topic and LTI systems, I have a set of slides which I will go through, but since this parallels what you have learned before, to see the similarities, and if there are any differences to note them down should not be very difficult. So system takes an input, operates on it or transforms it, and produces an output. And in typically this is represented as a block diagram as X. The system is represented by an operator T, and Y equals T of X is the output. And the notation X is general. It can either stand for X of T or X of N, based on whether you are looking at CT or DT systems. And typically Y equal to Tx is specified in the form of an input-output relationship. And here is one example of an input-output relationship. Here is another in continuous time that you may have seen. So this is a linear constant coefficient differential equation, whereas here this is a linear constant coefficient difference equation. And then here are two more examples in which the input-output relationship is not in the form of an LCCDE. Just to show that the input-output relationship is general, LCCDE is a very specific subclass of the general class. And properties that you would have seen in the context of continuous time can either be linear or nonlinear, time invariant or time variant. By the way, time invariance is also known as shift invariance. So LTI or LSI, linear shift invariant systems, is another common terminology. And system can be causal or non-causal, memoryless or non-memoryless. Memoryless systems are also known as static systems. And systems with memory, what's the other name that you may have known from your earlier course? The fact that the memoryless systems are called static should give you a clue. Dynamic. Okay. So non-memoryless systems are also called dynamic. System can be stable or unstable. Stability, of course, is a very important property for both man and machine. So we'll examine each of these properties in more detail. So we'll look each of these, define them and give examples. So typically, as you must have done exercises in continuous time, you would be given an input-output relationship and you have to test whether the system satisfies these properties. And to show that the system satisfies a property, you have to give a general proof. To show that it does not, just one counterexample is enough. So linearity involves two sub-properties which are not superposition. Yes, additivity and homogeneity. All right. So it has to be additive as well as homogeneous. Additivity is very simple. If x1 produces y1, x2 produces y2, you require x1 plus x2 to produce y1 plus y2, which means the system is additive. In terms of equations, this is the notation that is used. x1 plus x2 produces y1 plus y2, the system is additive. And this also brings in the notation, instead of using y equal to t of x, you can also use this notation. And this is another variant that you'll see in this context. So this is additivity. So here is a simple example, y of n equals x star of n. So if x1 produces y1, y1 in this case is x1 star, y2 is x2 star. If you now give it x3 of n, which is x1 plus x2, y3 is x3 star, x3 is nothing but x1 plus x2. Therefore, x1 plus x2 whole star is x1 star plus x2 star, and lo and behold, this is y1 plus y2. Therefore, the system is indeed additive. Okay, so here's an example of a system that is additive. Suppose you have y of n equals x square of n, then y1 produces x1 squared, x1 produces y1 which is x1 squared, x2 produces y2 which is x2 squared, and the combination is x1 plus x2. Clearly, x1 plus x2 whole squared is not the same as, does not produce y1 plus y2. So here is a system that is not additive. Therefore, this is not linear. And the other property associated with linearity is homogeneity. So if x produces y, then c times x must produce c times y, where c is an arbitrary complex constant, in which case the system is homogeneous. So these are the definitions, right? X produces y, c times x produces c times y for all little c belonging to the set of complex constants. So now let us take the previous example, y of n equals x star of n, and this system was shown to be additive, right? So if the input is now c times x of n, the output is input times, you have to take the input and complex conjugate it, correct? Therefore, the output is x1 star, which is c times x of n whole star, which is c star x star. Clearly, the system is not homogeneous. All right. So here we have a system that is additive but not homogeneous. Okay. Now let us consider this particular system. Y of n equals x of n minus 1 times x of n plus 1 by x of n, whenever the denominator is not 0 and 0 otherwise. All right. Now if you take an input x1 which is c times x of n, right, you see that y1 of n, when the input is x1 of n, x1 of n in turn is c times x of n, y1 of n turns out to be c times y of n, correct? So pretty simple, the c's cancel and you get c times y of n. So clearly this system is homogeneous, and one look at the definition, you can see that the system is, in terms of additivity, is the system additive or not? What can you say about the system's behavior when you add two signals? It is not, because you see x of n minus 1 times x of n plus 1, you have a product there, you will have cross terms. So this system which is homogeneous, very easy to see that this is not additive. So the point of this example is to show that additivity and homogeneity are independent properties. You can have a system that is additive but not homogeneous. You can have a system that is homogeneous but not additive. Only when both additivity and homogeneity are satisfied is the system linear. All right. So this slide just puts in writing what I had said in words, right? So the system is linear if and only if it is both additive and homogeneous. And somebody said superposition. That superposition principle captures in one statement both additivity and homogeneity. So you say that the system is linear if a1 x1 plus a2 x2 gives you a1 y1 plus a2 y2. Therefore, the system is linear. When you make that statement, you are capturing two sub properties together, right? You are capturing both of these in one statement, and this is called the principle of superposition. So when you say the system is linear, it obeys the principle of superposition, you are implicitly stating that the system satisfies both additivity as well as homogeneity.